Okay, number 4, and we're talking about the (1705) this is 04, isn't it? Class, and the document, and I have that here because I kind of need this list to remember what all these things are addressing. So the first, number 4, and I'm not commenting on the ones that I think are really obvious, commenting on the ones where you have a certain premise and you have to understand what that premise is in order to understand what to do. Okay, so number 4, you have the question of verify whether two functions are inverses, assuming you have the f of x and g of x form of the functions. It's just simply you got to show that f of g of x equals x and g of f of x equals x. Now there's more to inverse functions. You know, how do you graph them and so forth. And we'll probably come back through this list and expand on these ideas a little bit more. But right now we just want to talk about the general premise. So knowing how to do composites, it should be easy to do this if you're given the f of x and g of x form of a function and its inverse. Okay, number 5, you start with the idea that some basic function is given to you, some f of x function, and you want to form the a f of x minus h plus k function. So if I give you the values of a, h, and k, you should be able to take any of the basic functions and form this combination. So, for example, if f of x is x squared, then what is a f of x minus h plus k? You got to work from the inside out. First of all, f of x minus h you get just by replacing x by x minus h, and that gives you quantity x minus h squared. So a times f of x minus h is just a times x minus h squared, and a f of x minus h plus k is a times quantity x minus h squared plus k. And of course, that corresponds to a vertical stretch by factor a, horizontal shift h, vertical shift k. If f of x is 2 to the x, then what is the a f of x minus h plus k form? Well, a f of x minus h plus k, it's actually pretty easy if you just realize what f of x minus h is. If we replace x by x minus h, then we replace this x by x minus h, and we get 2 raised to the x minus h. And then multiply that by a, and then add k. There's our a f of x minus h plus k form of this function. Now you can do the same thing for 1 over x squared for any of the functions. And you just replace x by x minus h, multiply that result by a, and add k. And that gives you the form of the function that's vertically stretched from the original function by factor a, horizontally shifted h units, and vertically shifted k units. Hopefully you understand why that works the way it does, but you need to understand that it works the way it does so you can form these composites and know how to translate, shift, and stretch the resulting function. Number 7, it just says solve the given equation over complex numbers, given quadratic equations. Just to do that, you have to put the equation into the form ax squared plus bx plus c equals 0, and then either factor it, complete the square, or use the quadratic formula. Okay? Most often you'll use the quadratic formula in application, but in some cases you do need to complete the square, and in some cases you should do the factoring. And you need to know the connection between the factoring and the solution in any case. Find the vertex, axis of symmetry, maximum, minimum, etc., zeros of a quadratic function. The vertex is on the axis of symmetry, and the axis of symmetry is halfway between the zeros. That's your basic premise. The zeros you get by solving the quadratic equation. set the function equal to 0 and solve the resulting quadratic equation. That gives you the zeros. So cut number 7 gives you the zeros. Axis of symmetry halfway between the zeros. And even if you don't have real zeros, you have complex zeros, and it should be clear what number is halfway between those complex numbers, and that will be a real number, and that will be your vertex, or your axis of symmetry. Your vertex is on the axis of symmetry. To get the coordinates of your vertex, the x-coordinate will be the x-coordinate you get for the axis of symmetry, and the y-coordinate, you plug that x-coordinate into your function and get the y value. Okay. Your discriminant, number 9 says use the discriminant to determine if you have real zeros or not, how many real zeros you might have, or how many complex zeros for that matter. Okay, well anyhow, your discriminant is going to either be positive, negative, or 0. And the discriminant, of course, I didn't write it down in class because everybody should know, is the b squared minus 4ac, part of the quadratic formula, and I shouldn't have to write that down. This is either positive, negative, or 0. If it's positive, then you're going to get the plus or minus of the square root of that positive number, giving you 2 real zeros. If it's 0, then you know that the square root of this thing appears in the quadratic formula with a plus or minus. You're going to have a plus or minus 0. Well, plus 0 minus 0 doesn't make any difference. It gives you one solution. And if this is negative, then the square root is going to be an imaginary number, and your quadratic formula is going to give you 2 complex numbers, one for the plus, one for the minus. They'll be complex conjugate numbers, and your discriminant tells you all that before you even start plugging things into the quadratic formula, and that can be very handy. Okay, number 10, what do we use the transformations to construct a graph of a quadratic function. And your vertical stretch is A, horizontal shift is H, vertical shift is K. Your quadratic function, of course, is f of x equal x squared. So the stretch shifted function is of the form A times x minus h squared plus k. You simply sketch the graph of this basic function, vertically stretch it by factor A, horizontally shift it h units, vertically shifted k units, and there's your graph. Okay. Okay, so stop there for right now and move on in the next clip.